Hello everyone, my name is Tammie, and then I'm gonna show you how I do a spectral simulations of electrochromic glass in the Python environment. So this mainly use the spectral material modifier that Greg was giving the tutorial on Monday, and also using Towning's GenSky. So the goal of this is to spectrally simulate electrochromic tinting and then adding daylight dimming to it when you don't have enough daylight after you tinted to one of the lower tinted states. And then we also want to see the impacts on spectral irradiance and then on melanopic illuminance and then melanopic illuminance and then thermal load. So first I will show you how I set up the scene, so that mainly focus on the material primitives. And then I will show you how you interpret the intermediate tinted state. So I will be showing you the 60% rendering and then the 1% tinted rendering, and then how you interpolate the tinted states in between that and the dimming states between that. And then I will show you some of the results, and I will wrap it up with an animation. I noticed that, so on the leftmost image is actually having like a slight yellow hill at 60%. It shows up pretty white here. So first of all, how you will model spectral material that is opaque. So first you can download spectral material data from the spectral database that Austin built. So on the right, you're seeing what the website will be showing you. So this plot is showing you the spectral reflectance of a green leaf material. And then this, you will download it. And then on the website, they also have a radiance definitions, just a simple plastic primitive. So once you downloaded this data sets, it will have a list of spectral reflectance ranging from 360 nanometer to 740 nanometers. So that will be your extrema. And then you put in your spectral reflectance data under the spectrum material. So the spectrum material, I give it a name called greenleaf mat. And that greenleaf mat is supposed to modify this green leaf. So now it's no longer a void. You will actually have a material modifier for green leaf. And then as Greg was mentioning, on Monday, usually the RGB reflectance will be 1 if you want to keep the spectral data, but because the data on the website is actually in percentage, so I apply it to 0.01 instead. So how you will get the spectral material data for Windows. So you will go to the LBNL IGSDB website. And then on the website, they have the spectral transmittance data. So right here is showing you the 60% TVIS easy glass. So same thing as earlier, you build a spectral material type. And then here is your spectrum going from 380 to 780, and here are the spectral transmittance value, and you put it in, and then you use this EC60 to modify the glass material. Then to build the luminaire, you download your IES file from whichever manufacturer you like, and then you use the IES to rad function to convert the IES to Radiance primitive geometry and material. So the function will look like IES to rad and then -O. This is whatever name you want to name your file, and then the -DI is what dimension unit you want your file to be, and then this is the name of your IES file. So this function will generate a bright data primitive and a light primitive for your material, and then it will also generate a geometry for you, which I didn't include here. So to make this having spectral as a spectral material, what you do is the PNNL, so the Pacific Northwest National Lab, has a sample spectral lighting library. So I got one of their example from them, and then I built this light mat and then use that to modify the bright data material. So how you will build a scene, first you import Pi Radiance as a PR. So going on, we will be calling PR, and then what you will do is PR.scenes, and then you give it a name that you want to call your model, and then your surfaces, and then your materials. So on Monday, Tanning did give a quick tutorial of this. So if you want to know how exactly you want to do this, there is the walkthrough guide. So next, we will building the spectral sky. So by using Gen Sky, so how you would do that is you provide the daytime. So for this example, I'm showing you the the sky at noon on December 12th, and then this you by giving it latitude and longitude and time zone, the Gen Sky will give you the material definitions on the right. So this give you kind of the same thing that Gen Daylit will give you, and then with this sky func, you will want to build, using that sky func, you want to add your sky dome and ground plane, like how you would do in Gen Daylit. So after this scene is built, we're going to generate our HSR, that's our hyperspectral rendering. So what you would do first is that so what I use to generate the HSR is using RTPic. So what RTPic takes is that you put in your viewpoint, and then you put in your octree. So how you will build your octree in Pi Radiance is room, which is the scene that we built earlier, and then dot octree. This will build the octree for you. And then I'm using an 8 processor, and then this is the resolutions of the image, and then params is right here. That's basically the parameter you want your renderings to be. So this is render at ambient bounds 2. And then the two things to notice is this CS equal to 20. So that's the number of spectral channels that you're putting in, and then CO equal to true will give you the spectral output. And then this function will generate the HSR for you, but then it doesn't actually save it. So in order to save it, you got to write it to a file yourself. As Greg was mentioning, right now, you cannot open HSR in through Ximage. So one way to do that is that you convert it to HDR. So how you would do that is you use RCOM. So you first build like an RCOM input in here. We put in the HSR that we just built right here. And then the key thing to convert it from HSR to HDR is by calling the transform equal to RGB. So that's equivalent of your -C RGB in the regular command line. And then I downsample it and then save this HDR to a file. So this is how the HDR would look like. I kind of want to show like the color difference. Oops. So on the left, you're seeing the most clear state it has. So the TVIS is 60%, and then on the right is with the most tinted state at 1% TVIS. The runtime for each of them, it's about 5 minutes with a processor. And then this one, I render it with only daylight dimming to meet the target work plane illuminance of 500 lux. So in this particular rendering, there's only the electric lights, and then there's actually no sky in here. And then the runtime for this one takes a longer. I think it's because of the spectral luminaire material. So this one takes like 13 minutes. So how will you combine the electrochromic tinting with daylight dimming? So on here, we have the clear state 60% electrochromic tinting. If I want the tinted states in between 60% and 1%, supposedly if I multiply the clear state by a tinted factor, it should give me the 1% or whatever percent in the middle that I want to. And then to implement daylight dimming, I have the fully powered electric light there, and then I multiply by a linear dimming factor that compensates for the insufficient amount of daylight in the work plane luminance. That should, when I add the two together, the electrochromic tinting and the daylight dimming, it should give me the rendering on the left. So in here you can see the luminaire and then the electrochromic all in one nice photo. So the electrochromic tinting curve, this one is just like a sample one that we do on simple exponential function. So y equal to a times b to the power of x. So on the left, you're seeing the spectral transmittance of each tinted state. So each line is representing a tinted state. And here there are a total of 180 tinted states because I'm trying to make a video, a 1 minute video, and then there will be like 3 frames. So that goes to 180 tinted states. And then you can see that in the beginning, the tinting is much faster, like the drop in visible transmittance is much at a much faster tint, and then it decreases as it gets darker. So on the right, you can kind of see this exponential curve for the tinting. So how do you do that in a script to combine the electrochromic tinting and daylight dimming? So we'll be using RCOM to combine the two. So first, you're gonna build your RCOM input. So we have that tinted HSR that we render, and then you are going to apply the tinted factor from this curve. So there will be 20 scalars mapping to the 20 channels that we're interested in, and then the same thing for the dimming part. So for the dimming HSR, I also apply 20 scalars to dim it spectrally. So to combine them, you just put the two RCOM input, and then you add the transform equal to RGB to convert the HSR to HDR. And then once you have the HDR, you downsample it with P-field, and then you save it to a file. So once you have the downsample combined HDR, you want to add tone mapping to adjust it for human vision. So how you would do that is PR.pcon and then with human equal to true turn on. So this is what the result would look like. So this is showing spectral irradiance. So the key thing to generate this, the key thing to get a spectral irradiance is through using R-trace. So just like RT-Pig, you are going to provide your viewpoint and then your octree and then the parameters right here. That is showing above, same thing, CES will be equal to 20 channels, and then spectral output will be equal to true. And then another thing to notice is that we are interested in irradiance, so you gotta turn irradiance equal to true. So on the right, we are seeing on the blue curve, the TV 60% is gonna dim all the way to the 1% noted by the orange line right here. And this plot is showing irradiance versus wavelength, and all the gray lines in between, we're gonna interpolate them. And this is showing photopic illuminance and melanopic illuminance. So how you will get that data also is using R trace. And then key thing to know is that you turn on -PY for photopic illuminance, and then -PM for melanopic results. So on the plot, you're seeing illuminance versus time. So left is vertical illuminance photopic, and then on the right is the melanopic lux. Another thing, I kind of throw them into this bucket of like irradiance modeling is thermal load. So how we are gonna calculate thermal load is using PyWinCalc. So that is LBL's based on the LBL Windows machine. So you will use PyWinCalc to calculate the solar heat gain coefficients of the electrochromic TV 60% and 1%. So the formula for thermal load will be equal to thermal load equal to solar heat gain multiplied by your incident irradiance. So how you will get the incident irradiance is that we will just need to build an empty scene with the Gen Day lit sky, and then you're gonna place your sensor at place your sensor at a viewpoint that is facing the same direction as your window. Then you will get the incident irradiance of the scene. And then for PyWinCalc side, we need to put in environment data. So this is pretty standard variable that you will build for the inside-outside environment. The key thing to notice that I changed in the PyWinCalc example file is the air temperature that makes it more accurate for the Berkeley weather data, which is where the sky is modeled to. And another thing is the direct solar radiation will be the incident irradiance that we just compute. And the example where this whole file is located is in the PyWinCalc GitHub page. So we will also need to build a glazing system in PyWinCalc. So same thing, you go to the IGSDB website, and then you download a JSON file that has all the solar and all the solar data, and then it will it will generate a glazing system based. You put this JSON file into your glazing system, and then PyWinCalc is gonna build that window system for you, and then you just do a dot solar heat gain coefficient, and then you will get the coefficient for this specific glazing system that you build. And then you multiply the solar heat gain by the incident irradiance, you will get your thermal load. So here is an animation of all the results that we just mentioned. Maybe. So some of the things that you might want to pay attention to. So this is the HDR rendering, and then this is the false color. And then right here, this plot is showing the irradiance versus wavelength plot. And then on the most right-hand side, the top is showing photopic illuminance, below that melanopic illuminance, and below that is DGP, and right below that is the thermal load. And then we can look at it once again. And also kind of towards the end of the video, you will see how daylight dimming is activated, and you will start to seeing the luminaire in the scene. Some additional information. This is how you will model, convert your HDR to a false color image, and then you can just do simply by calling false color, or then there's the matplotlib with that Towning showed the other day. And then this is how you will convert the HDR image to a PNG and to put the animation together. So that's it. The workflow is posted on the GitHub page in case you want to take a look, or just the video is also on there. Thank you. So right here, you're seeing the tinted curve for each of the like waveband, like the 20 waveband. So you can, like you said, they're actually not a uniform curve for each. Um, so we didn't actually use a like we make our own wave. Yeah,